Okay, so this is lecture 3 of operational amplifiers. This lecture will study the folded cascode differential amplifier as a potential operational amplifier. So the first thing I want you to do is draw a folded cascode differential amplifier. Alright, you have drawn the telescopic cascode differential amplifier. Now you just pause and draw the complete circuit of a folded cascode differential amplifier. It's very important that you learn what this looks like without or before I show it to you. Okay, so here is the circuit. So we had seen the folded cascode single input. This is a differential. So let's look at this circuit. So this is of course M1, M2, M11 is the differential pair with the tail current source. Then for a folded cascode, what happens is if the input transistor is an NMOS, then the cascode transistor is a PMOS. So what happens? The output of the input transistor is connected to the source of a PMOS, and the output of the PMOS is the output of the amplifier. So both are possible outputs. I have taken this one. Alright, so the common source stage M2, common gate stage M5, and similarly M1 is common source, M6 is common gate, and the output is here, and the loads are cascode loads also. And if you recall from our discussion on folded cascode single ended input, there is a transistor required at there are transistors required at the top to provide the current to both these branches of the folded cascode. The M2, M5, the current is provided by M3, and similarly for M1, M6. Alright, so this is a folded cascode configuration. Now let us look at this configuration in a closed loop unity gain feedback circuit. So let's see what I am doing. Okay, a couple of comments which I have made before. So let's go back here. M3, M4, the current in M3 is equal to the sum of the currents in M2 and M5. Therefore, M3 carries about, well, if these currents are equal, then twice the current of M2 or M5, and therefore M3 and M4 are larger transistors than the rest of the transistors. Qualitatively, right? These currents are not necessarily always equal, but M3, M4 are certainly larger than M5 and M2. The other thing is a design of a folded cascode makes an excellent test question, right? So please study and spend some time designing a folded cascode on your own. Okay, now let us put this circuit in unity gain feedback. So okay, so the first question we ask is we want to connect the output to the negative input of the differential amplifier. So first we have to determine which is the positive and the negative. So let's look at this one. So if this is the input and if this is positive, then the drain is negative. If the drain is negative, VO is positive, which means that V2 is the negative input, V1 is the positive input. Alright, so plus minus. So you want to short the output to the negative input terminal and study the output swing. This is what we want to do. Alright, so here is the circuit. So we short the output to the negative input circuit. Alright, and now let's put numbers. We'll put the same numbers as last time we did for the telescopic cascode. So we said the threshold voltages are 0.1, overdrives are threshold voltages are 0.4 volts, overdrives are 0.1 for all transistors, and so the VGSs, which is VT plus VOV is 0.5 volts for all transistors. And with this we put numbers. So it's a VG9 is 0.5. If VG9 is 0.5, then VG7 could be 0.6, but I have made it 0.7. Alright, if this is 0.5, this could have been 0.6, but I have made it 0.7. VG3 is 2.5 because the VGS is 0.5 here. Vg5 is again this could have been 2.4 but I made it 2.3. Alright, and with these numbers, and Vg11 is also 0.5 volts. Alright, so with these numbers we ask what are VO min and VO max. So you please pause and calculate VO min and VO max with this short circuited, right? That is what is critical here. Okay, so we'll look at VO min first. So we say what is the lowest voltage that can exist at this node while keeping all transistors in saturation. So we clearly see that when VO goes low, M7 may go into triode, nothing, M5 will not be affected. So M7 we have to look at, and if VO goes low, that is the gate of M2. So as we studied for a telescopic cascode, this may drive M11 into triode. So two paths we look at, we find the two VO min. So VO min for M2, in fact we did this last time, it is the same as last time. So it is 0.1 for M11 plus 0.5 for M2. So 0.6 is the minimum that must exist at this node to make sure that M11 stays in saturation. If it goes below, M11 will go into triode. For M7, to stay in saturation, the drain voltage has to be greater than Vg7 minus Vt. So this is Vg7 minus Vt, which is 0.3 volts. So we take the higher of the two, so we say 0.6 volts. So the VO min that must exist is 0.6 volts. Let's look at VO max. So for VO max, what is the highest voltage that can exist at this node? We say, well, M5, as a VO increases, M5 may go into triode, or as this VO increases, M2 may go into triode. Alright, because the gate voltage will become higher than Vd plus Vt. Alright, so M2 is a Vd2, which is this voltage, which is the same as Vs5 must be equal to Vg5 plus Vsg5. Okay, how much is Vd2? Vg5 plus Vsg5. Alright, so Vg5 is 2.3 plus Vsg5. Vsg is 0.5 for all transistors, so 2.8 volts. So Vd2 is 2.8 volts. So for M2, this is the gate voltage of M2 that has to be less than Vd2 plus Vt. So 2.8 plus 0.4, so 3.2 volts. So this is okay, this is not even a limit because nothing is going to go above 3 volts. So we are safe from M2. M5, for M5 to stay in saturation, VO has to be less than Vg5 plus Vtp. So Vg5 is 2.3 plus 0.4, so VO max is 2.7 volts. Right, so VO max is 2.7, VO min was 0.6, so our output swing is 2.7 to 0.6 volts, which is a good range. It is, as I said last time, this range never becomes 3 volts. 2.1 is a good range. This can be made larger. Let us think about how we can make this larger. So as I said just a few minutes ago, let us go back. So here this Vg7 could have been 0.6 and Vg5 could have been 2.4. So by making these 0.6 and 2.4, we can increase the range by 0.1 volt. In fact, specifically by Vg5, right? So here this 2.7 was because Vg5 was 2.3. So if we make this 2.4, this becomes 2.8 and we increase the range by 0.1 volt. Alright, so this can become 2.8. This 0.6 is a kind of the bare bottom minimum possible. We cannot reduce it because 0.6 is Vt plus 2 overdrive voltages. So let's go back here. So these are the Vt of M11 plus the 0.1 of this and 0.1 of this, and there is nothing we can do about 0.1. We cannot make the overdrive less than 0.1. and therefore this voltage is the bare minimum that is required. So 0.6 cannot be reduced any further. Alright, so we can raise this to 2.2 volts, but that is the upper limit, which is good enough. Alright, so okay, so a couple of side comments. Let us remember that the DC gate voltages that I have put here. So these gate voltages 2.5, 2.3, 0.7, 0.5. When we actually design a folded cascode, these voltages will be generated by current mirrors, right? You recall, we don't put fixed gate voltages in MOSFET circuits because VT will vary and then currents will vary if there are fixed voltages. So instead of fixed voltages, we put current mirrors. So these 4 voltages would have to be generated by current mirror circuits that would have to be designed to complete the design of the folded cascode amplifier. And the voltage values that we have used, 2.3, 2.5 and 0.5, 0.7, would require that the mirrors we build will have to be low voltage cascodes. The regular cascodes will not work. Alright, this is just a side comment to kind of comprehensively think about the design of the folded cascode. Okay, because of this property of a good output voltage swing, folded cascodes are used widely as single stage high gain operational amplifiers. Now let's do a quick comparison of the folded with the telescopic. Just kind of, this is more an academic exercise more than anything else. And in a way it is also a revision of everything that we've done till now. So telescopic cascode, the differential mode gain, the half because it's a differential mode, GM into the output resistance, which is GMRO squared parallel GMRO squared. So I'm doing an order of magnitude calculation. So I'm assuming that all the GMs and all the ROs are equal. This is just to get a qualitative picture. In real circuits, they are hardly ever equal, but it gives us an order of magnitude idea. So the gain of a telescopic is of the order of GMRO the whole squared by 4. The gain of a folded, you recall we had derived this when we studied the single stage, a single input folded, is GMRO squared parallel GMRO into RO parallel RO. So maybe we should go back and look at this. So the no, not this one. So okay, ignore the shorting of the output and the input. Without that, the output resistance of a folded cascode is the resistance looking down, which is GMRO squared right here, in parallel with GMRO of M5 times the resistance looking at this node, which is the RO of M2 and RO of M3 in parallel. So RO parallel RO into GMRO. So that is where this GMRO, RO parallel RO comes from. So if all this put together, this comes out to be GMRO the whole squared by 6, which is of course smaller than the telescopic cascode gain. Alright, let's also quickly look at the frequency response of a folded cascode. We actually did not do this in chapter 6. Let us do it now. Maybe frequency response is too exalted a term. What we'll look at is simply the time constants associated with the nodes for the folded cascode circuit. So I'm just finding the time constants for the half circuit of the folded cascode configuration. So this is when the input applied is a differential input, so that we can draw the half circuit. What are the time constants of the various nodes? So there are 4 time constants, 1, 2, 3 and the input. And for this discussion, I'm assuming that the input time constant is small by assuming that the input resistance is small. So we'll look at 3 time constants here. So let's write expressions for the 3 time constants. So at the output, the time constant tau 0 is the resistance R out into the capacitance at this node. The capacitance at this node is 4 capacitances, 2 from M5, CDB5 and CGD5, 2 from M7, CGD7 and CDB7. So that is here, and I have written N and P instead of 5 and 7. R out is GMRO squared by 3, as we just saw. The resistance of a telescopic cascode at the output node is GMRO squared by 3. This of course is very large. All other the other two nodes have a resistance of the order of RO, and so this is GMRO times larger. So this time constant is the largest time constant in a telescopic cascode circuit. So this time constant dominates the frequency response because it will give the smallest pole frequency. Okay. At X, the time constant is Rx times Cx. Rx is the resistance seen at the node X. What is that resistance? It is RO parallel the resistance looking down of M5. The resistance looking down of M5 is the resistance looking down the source of a MOSFET, and if you recall that resistance, I'm going to say it aloud because you've seen it many times before. It is RO5 plus the resistance seen down from the drain, which is GMRO squared. So RO plus GMRO squared divided by 1 plus GMRO of M5. Okay, so that is approximately GMRO squared by GMRO, which is RO. So this is RO, another RO, another RO, so RO by 3. So the resistance of at this node is of the order RO by 3. The capacitances are many, right? So you have CGD2 or CGDN, CDB2, CDB3, CGD3, CGS5 and CSB5. Alright, so there are 6 transistors, 2 associated with each of the 3 transistors connected at that node. Now, as I noted a few minutes ago, M3 is a larger transistor because the current through M3 is the sum of the current through M5 and M2. Because M3 is larger in size, its capacitances are larger. Therefore, the overall capacitance at this node will be larger than the overall capacitance at the node Y. And the resistance at node Y is in fact equal to RO by 3. And therefore, tau x, the time constant at this node, is larger than the time constant at the Y node. So this is the second most important time constant, and sometimes called the first non-dominant time constant. This is the dominant, this is the first non-dominant time constant. And then the third time constant is at the node Y, which is RO by 3, and 4 capacitances of these 2 transistors, 2 each from M7 and M9. So tau Y will give a third pole. And as I said, we'll ignore the pole at the input terminal. Now if we compare these time constants with the telescopic time constant, and I'm not doing this, you should do this comparison. Of course, the gain of the, as we just saw, the gain of the folded cascode is slightly smaller compared to the telescopic. The dominant time constant of the folded cascode is slightly smaller than the telescopic. Why? Because the output resistance of the folded cascode is slightly smaller, so the time constant is also smaller. The first non-dominant time constant of the folded cascode is slightly larger compared to the telescopic because we have a larger size transistor at the top. All this put together leads to an overall poorer frequency response. I'm not explaining this. We'll look at this more closely in the next chapter. But the folded cascode has a slightly smaller gain, slightly poorer frequency response, and yet it is the folded cascode that is used widely as a single stage op-amp, and telescopic is never used as a single stage op-amp solely because of the output voltage swing under closed loop conditions. All right. Okay. Yeah, one more note. So if you look at this circuit, where is this circuit? The op-amp. Now let me go back to this one. So this circuit is naturally a circuit where the output can be taken differentially, or the output can be double-ended. So these are both telescopic and folded naturally are circuits that where the output can be either single-ended or double-ended. All right. So as I said, I'm just making a comment. We're not really going to discuss double-ended output uh, operational amplifiers. Okay. So that is this chapter. I'm sorry, this circuit, this lecture. Next lecture, we'll look at a simple two-stage op-amp.